have Dr. Mike Robinson from RealD. Mike has a bachelor and doctorate degree in physics from University of Oxford. He worked as a postdoc at Oxford University, and then he moved to Boulder to work here at CU as a research assistant professor. Then he went back to Oxford to work for Sharp Laboratories of Europe, where he specialized in digital projectors. He decided that Boulder was better, so he came back to Boulder and joined ColorLink, which was a CU-seeded company that developed and manufactured retarder-based polarization filters. He didn't change company, well, because his company, the company he was working there got bought by RealD. That was about 3 years ago. He's a chief scientist at RealD, and his primary responsibility is the development of consumer display technologies such as 3D TVs. He's also involved in other aspects of 3D technology, including this exactly stereoscopic capture. So, thank you for coming.
Thank you very much. Yeah, so I was here 21 years ago, a long time ago now, and the company that I joined the second time I came here was actually a spin-off of the Optical Computing Systems Center, as it was then. And we represented success, I think, because we took the technology that was based on some experiments in a laboratory and gradually built up the technology until I purchased a television at Costco with our beasties in it. In fact, it's in my living room at the moment. So unfortunately, perhaps, that particular line of product, which was a projection television, died away. But we were able to change and make hardware for 3D cinema, which, as you're probably aware, has been resurgent in the last year. And RealD, who started us off on that path, bought us 3.5 years ago. So I now work for RealD. The R&D center of RealD is based here in Boulder, which maybe people don't realize. And excuse me, we employ about 70 people, of which 30 are technicians. We actually make the hardware in the building, just behind the post office, next to 55th and Valmont. So, because it's relevant to engineering here in Boulder, I want to talk a little bit about the emergence of RealD, and then I want to talk a little bit about display hardware. Now, the display hardware is actually my forte, as it were. This is what I do. But today I'm going to go on and talk a little bit about something that interests me and I've done a bit of work on. And in fact, the work I've done is going to be employed in what we call our gaming solution. Sometimes we call it a gaming toolkit. A game will be released next year using this solution. And the solution is to do with CG correction of stereoscopic capture. And I'll point out why that is necessary. So let's go in, first of all, RealD. This is a slide that is often presented. The global leader in 3D. Okay, so we're not short on blowing our own trumpet. We are able to say that, though, because we are solely 3D, and as far as I'm aware, we are by far the most, what's the word? Our income is greater than anybody else in 3D, by a long way, okay? But we actually do more than cinema, okay? The cinema experience that I hope you've all had, wearing our glasses, we have our logo on the side, is the main earner, but we are actually, wherever visual media is displayed, RealD makes the experience more lifelike, immersive, engaging. Okay, this is a bit of sort of market speak again. But the idea is that we actually do more than just the cinema, and we're actively involved in the next stage, which is to try and bring it into the home in particular. Okay, so where we came from, well, even though RealD has had a very fast growth, it dates back from 1980. And the reason it dates back from 1980 is that ColorLink, the company that I worked for and was bought by RealD, is not the only company that RealD bought. RealD bought a company called Stereographics. This logo here, some of you might recognize if you've done any 3D before. Stereographics was set up by somebody called Lenny Lipton, And Lenny Lipton is known in the industry as the father of 3D, partly because, well, I hate to say this, he's relatively old and therefore has been around for a while and started it very early on. But he did pioneer many of the things you see now. The shutter glasses here, called Crystallize, are still being used, actually, for 3D simulation. When I came here, I can't remember, about 7 years ago, I visited the BP Visualization Lab, and they were using these things. The Mars rover that went and took stereoscopic pictures of Mars, which is still on the internet, used cameras that came from Lenny's company. Lenny, however, well, he was involved in Piranha 3D more recently. He's left RealD. But his main claim to fame, actually, is that he wrote the words to Puff the Magic Dragon. So you ought to look that up on the internet. Lenny is a good friend of mine. So anyway, he started all this. And while this was going on, which he was primarily an inventor, let's say, and chugging along, making enough money to keep a small factory in San Rafael running. In 2003, RealD was founded. And RealD was founded by two people, Michael Urs and Josh Greer. And they claim they spent 2 years in a windowless room. I don't believe that, but in order to come up with a business plan for 3D. They believed 3D cinema was ready to go. And so they managed, I think, to time it well. Either that or they had some sort of influence on the world. Because what happened was that they tied in with various things, like the cinema audience was going down because people were buying bigger TVs. And so there needed to be an incentive to bring people into the theater. There was a huge push to get rid of film. They wanted to get the digital media in there. And so, and then Disney produced Chicken Little, which is a film that was the first 3D film to be produced. And I think you probably don't remember this because it's sort of but Disney felt that it was going to go in 2D, so they thought they'd turn it into 3D. And they turned it very crudely, but nevertheless it was 3D. And RealD promised that we would have, or they would have, 100 cinemas. And they did that because they'd contacted Colorlink, which is up here, the company here in Boulder, to actually make the product. But they told us with, I can't remember, but it was like, a few weeks or something to produce these things that we'd just been specified and to come up with 200,000 pairs of glasses, and there was a world shortage of polarizer. And anyway, we said, okay. We managed to say that because actually Colorlink at that stage had a factory in Japan, and we knew where there was polarizer in the Far East. And so we said, your glasses, $5 each. And they went, well, $5 each? No, we'll go somewhere else. They said, well, of course they couldn't go anywhere else. So in the end, they actually bought the glasses off us. The product we made, which are in the cinema, still in the cinema today, of these particular systems. So the reason we were able to do that is that Colorlink spent a lot of time developing the technology that we're now just taking out of our top drawer and putting it together. So it's not as if we were able to conjure this out of thin air. We've had about 7 years of making liquid crystal devices that were robust, fast, had good field of view, had low scattering, had durability, et cetera, et cetera, et cetera. And so it's something that was very fortuitous. And we were phoned up by them. I have to give them credit for finding us on the internet. So there you go. After 3 years, 2 years, 2005 and 2007, we were their sole vendor for various things. And that relationship, in the end, forced them to buy us. And so we were bought 3.5 years ago, and since then things have gone better and better and better, and of course it culminated with the film Avatar, which was a huge success, and because of that success the demand for 3D screens went up tremendously, and we don't supply hardware, we don't sell the hardware, we sell a service. We say to theaters, we will keep you up with 3D technology if you give us an upfront fee and we get so much revenue for each ticket. That has turned out to be much more lucrative than selling hardware. So if you guys are going to make product, it's very difficult to make money selling things, especially when things get commoditized, whereas services deliver much better return. So following this, we had to raise money in order to give out the equipment initially, because there's an upfront fee from us. And so on July the 16th, RealD went public, and we're under the RLD sign on the New York Stock Exchange. Now that is very rare for a company to go all the way to the stock exchange. I think it's 1 in 10,000 or something. So, a great success. Right. The cinema system is the following. We have the basic system is a projector, single projector. Unlike IMAX that has 2 projectors, which is aligned very carefully on the screen, so that what you see in one eye is coincident, certainly in the vertical direction, with the other eye. We don't have to worry about that. We have a single projector because we do things time sequentially. This projector is able to produce frames at 144 frames a second. The data, which is still filmed at 24 frames a second, for reasons that is interesting, longevity of these various things, standards in Hollywood, that is not fast enough to avoid flickering if we supply a left eye image followed by a right eye image followed by a left eye image, because each eye would then see a 24 hertz signal with a 50% duty cycle, which is tremendously bad in terms of flickering. The 30 hertz is about the worst you can get. So in order to get a flicker-free experience, we actually triple flash. We put a left eye image followed by a right eye image followed by a left eye image followed by a right eye image, and the 3 left eye images are the same, followed by 3 right eye images are the same before we go into the next data frame. And during that 144th of a second, or sorry, between those segments of 144th of a second, we must switch this liquid crystal switch between one polarization state and another polarization state, so that you're able to discriminate. Your eyewear blocks one polarization state and the other one blocks the other one. So off come these frames in time hitting the screen. If you take your eyewear off, you can't see any difference because they're coming very, very fast, but they are coming time sequentially. You will see both left and right eye frames if you take your eyewear off, which is where you get these double imaging. However, as soon as you put your eyewear on, you will see the correct right eye in your right eye, left eye image in your left eye. In order for that to work, though, the screen is part of this system. The screen has to be a polarization preserving screen, and at the moment we have sprayed screens with metal in it in order to give you the polarization preserving. That process is one of the developments that is getting better and better. And currently these systems run at around about 100-to-1 contrast ratio, which is the contamination of left to right eye. Okay, so this is what it looks like. This is the original so-called Z-screen, the liquid crystal shutter. Behind here is a great big projector. These things for cinemas put out 50,000 lumens. That's wrong, it's 10,000 lumens, isn't it? 10,000 lumens. They are about this big, about this high, with a huge vent that comes out the back. And they're called cannons because the size of the lens coming out the front is literally about 20 centimeters in diameter here. In front of this we have a shutter which is so big. And that shutter has a polarizer, as drawn here, that blocks out half the light, because this projector, being a fast projector based on a technology that actually has little mirrors that flip. I noticed outside you've got a mosaic of fluttering mirrors. It's a bit like that, but they're electrically controlled. That's another story about that technology. But that's what's actually inside this projector, is 3 of those, 1 for each color. And they do everything digitally, so they build up the image out of ons and offs of intensity as a function of time. It's a very fast projector, but it's unpolarized. The light coming out of here is not polarized, and in order to produce a polarization state, the first thing you need to do is to clean up the light. So you end up putting a polarizer in front, and that loses 50% of the light. And that put the brightness down to the level that your eyeball is starting to lose color fidelity. So the original systems were quite dim. More recently, and I was involved directly in this, we've introduced this beast here, which is a polarization preserving element. We call it the XL, where light goes in the back. You can't see it very well. There's a little hole in the back here. And there's a mirror here, and this mirror is a polarization selective mirror. It reflects S polarization up and transmits P polarization, so that you end up with 2 beams of opposite polarizations. Now you can never, well, before I get too far, what you do is you transfer the polarization of this upper beam to be the same as the output beam. So now you have a beam of light which is the same polarization. However, you can never put them on top of each other again, because that's this business of constant brightness. It's one of these entropy things. So you end up having to contain the image, the light, which is going to form the image on the screen, as two separate beams. They converge onto the screen together. And because the path length here is slightly different, you have to do some refractive correction, so we have a lens element in there. And all this has to be operated, as it were, or put on when you show a 3D movie and taken off when you don't, by a projectionist. And projectionists are not very well trained. I don't know whether any of you guys do it in your spare time, but there is not a lot of training. Therefore, it has to be pretty robust. And it's surprising that if you do have parallel mirrors like this, one of which is the beam splitter, one of which is the other one, it is terribly tolerant to doing this, surprisingly so. So it turns out that this unit is very user-friendly for the cinema. This more than doubles the light of this one. This one puts us ahead of our competition significantly in terms of the brightness on the screen. So that's what we do at the moment. The future is all about this stuff. This is actually what I do from a day-to-day basis. These are the systems that are being advertised at the moment. We are involved in this particular aspect of it, the active eyewear. We have designs that stem back, of course, from Lenny Lipton's Crystallize, the first set. But because we've been designing liquid crystal cells and their compensation for years and years and years, we do have the best lenses that are out there. We want to go here. It looks the same, but the difference is the eyewear. This is passive eyewear. If you take off I didn't explain this. These are shutter glasses which allow transmission half the time in one eye and then oscillate this way, so that if you can get a TV that presents images fast enough, then you can see a right eye image, followed by the left eye image, followed by the right eye image. So these are active shutter glasses. They have liquid crystal cells in the lenses themselves. But they require batteries and they're heavy.
What's the switching rate?
Well, most TVs in stereo run at 120 hertz. So, and that's the flicker-free, left eye, right eye, followed by a different left eye, followed by a different right eye. So 120 hertz is the stereo. The TVs are often spec'd higher than that. They put black frames in for suppression of crosstalk between the two. So we often use televisions that are faster than the 120 hertz native. But nevertheless, the data going to the eye never has to be faster than that. And it's just more difficult to do things faster. Here, if you take the shutter, as it were, off the eyewear, you have to do something like what we do in the cinema. We have to do something on the television. And there are various ways of doing that. The one here, which is a JVC, actually modulates alternate lines with different polarizations. It's called an X-pol technology. And so you end up with odd lines being seen in one eye and even lines being seen in the other. Surprisingly, it's compatible with our eyewear. It's surprising, actually. Okay, so this is where, fortunate, of course, but surprising. This is where people would like to go, and this is to do with no eyewear at all. And it's very, very difficult. This is the Nintendo DS. The latest one is going to come out in 3D. I'm involved in trying to produce devices that are so-called autostereoscopic. The problem, though, as you can imagine, is that somehow you have to discriminate between what you see in this eye versus what you see in the other eye. And you'd like to have it so that when you look around, you can look around objects, which is extremely difficult, as you can imagine. One way of doing it is to do everything spatially, so that you have all the information of all the images on the display. And whatever you put on the display is able to simply show some of that information, one image, at one angle, and then a different set of pixels, a different image at another angle, and so on. And because your eyes subtend different angles to a small display, then you end up being able to see two different images in your eyes, and also maintaining that difference of eyes, plus what we call the motion parallax, the movement of the object in 3D space as we move the thing. So that is possible, excuse me, but the data, the amount of pixels you need in this is actually very, very frightening. And so that is still very much, it's doable, by the way, from a scientific point of view, from a physics point of view. But this is happening and will progress gradually, but it's still a long way down the road before you get a television that's with no eyewear. Okay, so now I'm going to go on to what I was going to talk about, which is capture. And to understand capture, I'm going to step back a little bit. I've assumed throughout that people understand why we see 3D when we go to the cinema in this case. And it's all to do with this stereopsis, which is the consequence of if you have an object. Let's imagine this is a top-down view, as you can imagine. This is a cone or a pyramid. And let's say you're looking at the top of this pyramid. If that was a real object, then your eyeball here would see that point along this line. You could put this point anywhere along this line and the image on the retina will be the same. Likewise, with your left eye, if that point lies, that object slid up and down this line, you wouldn't really tell any difference in your eyeball to first order. So, if you produce an image on a screen that the point of this is along this line for your left eye and along this line for your right eye, then it looks like that object actually exists where the original object was, even though it is represented by two images on this plane here. And so that simple geometry is why we see what we see with 3D. And all we've got to do in some sense is to produce two images that have the correct separations for the different objects. And because we're going to look a little bit at the math of this, I've thrown in a few things. Typically scenes have a closest object you see and a furthest object you see. And I've used sigma to indicate the perceived depth of these objects from your viewing position. And your viewing position is at a particular distance from the screen. The screen is a certain size. And for any given object, there is this disparity, I call it. It's a separation of the images. And that separation of the images is the encoding of where these objects exist in space. So separation means distance, albeit not a linear relationship between the two. So that's the sort of geometry. So how do we produce it? Well, this is maybe the obvious, certainly the standard way of producing stereo imagery, and that is to take two cameras and to put your objects, where they are, and to take two photographs. And then those images are placed on the screen, and that is your stereo image. Now, to do that, and to just go around some of my relationships, I'm going to define a real minimum distance from the camera, and a real, remember I used sigma before, I'm now using big Z, it just happens to be the notation I use. So we have a scene depth, we have a virtual screen plane, we have a camera size, this is the CCD size, and based on the size of the CCD and the lens, you will capture a certain angle. And based on all this geometry, and I won't go into details, you will produce two images, and lo and behold, if you put them on, you will see some sort of 3D. But you can change things. For the given zoom setting, which determines your 2D image in some sense, you can do certain things to your second camera, assuming you're matching the zoom. And the two things are A and B in this diagram. One is to separate the cameras more or less. And the second thing is to, in this case, adjust the sensor of the lens relative to the camera relative to the lens. These are two independent adjustments. In fact, the second one of these adjustments is, I call it D, all right? This expression here relates A and B to something called D. D is, in the end, how far you take an image and move it on the screen. Okay, so assuming you've taken the left and right eye image, you put it on the screen, if you separate the images by an amount, that is what I now call as D. All right? So in the end, we have A and D are the two things you can do, but D you can do afterwards. Okay? So you have camera separation and you have what's called film offset. But you can do D in what's called post-processing. If you do filming, you typically do a lot of things on set and you do things afterwards. So in the end, you have to get the camera separation right and you can do the rest automatically. So that is what you need to determine for any given shot. I should say also that the film offset is equivalent to bending the cameras this way. But if you actually tilt the cameras this way, you introduce what's called keystone distortion. So the images are no longer, you can't align them horizontally. So you end up with vertical disparity. So it's better to actually shift the images horizontally rather than... Okay, so let's have a look at what the first order effects of A and D are. Well, if we're going to capture these objects, we've got two cameras. You're going to see them, as we saw before. We're going to see them with a screen. And we're going to have a perceived scene depth, and I haven't put the math in here. So if you adjust A, this is what happens. All right? So if you take two cameras, you keep the zoom setting, you take one photograph here, one photograph there, you had the original scene. You simply separate the cameras, you take one photograph and place those on. What happens is the objects that are closer to you come closer, and the overall scene depth gets much, much bigger. So there's a sort of extending of the whole overall images. So if you get a flat scene, like in Hollywood, a lot of people complain that the 3D is not enough. Well, they should separate the cameras more. Maybe. I don't agree with that, actually. But that's what you have. Now, if you increase D and hold A, simply separate those same images now across the screen relative to the other. You push everything out this way. So you now have a handle over where your objects exist in 3D space. And so when you're taking a film, you have to think about that. It's not as simple as saying, I like the look of that picture, I'm just going to take a photograph. You have to say, I'm going to take this photograph, which I like the 2D, but now I've got to think, where are these images going to sit on my final display, and how big is the display, and et cetera, et cetera, et cetera. So it's actually quite an overhead on the capture. In fact, in general, this is just geometry, okay? This says that your perceived depth is a function of your real depth, which relates to, well, your eye separation, which is interesting in itself because, you know, it's amazing that it works for kids as well as adults. The difference between your offset and your eyeballs, which is an intriguing term here, where you are from the screen. If you go further back from the screen, things get bigger and bigger and bigger. As you go closer, they get flatter and flatter and flatter. All right? Now, when you're in a cinema, because the motion you have is so small compared with your distance, it's much more forgiving. If you have something like this, you can cause objects to really extend or not, depending on how far away it is. That's unfortunately a consequence of the geometry. It also is a consequence of zoom. Zoom, well, zoom is zoom, okay? You don't have to worry what this means, but it means that there is a zoom associated with when you look at pictures. If you hold up a frame like this, and I look at an object, let's say there, it has a certain size, it fills the frame, I am viewing it with what can be defined as a zoom angle, a half capture angle. Then there's the point of bringing up your camera and taking a photograph of it. And it may be that when you take your photograph, you're having a certain zoom, and you're going to view it on a photo frame this way, this far away from you. So the viewing zoom is different from the capture zoom. That is absolutely standard for 2D. In fact, it's a real problem because 2D is wrong, all right? It is wrong most of the time. And I'll come to why that it is wrong. So, can it ever be correct? Given that I've just drawn, oh, sorry, what I didn't say is that if you just plot this function for a typical set of stuff, then you often get this, okay? This is where your perceived depth and your actual depth is somewhat distorted, okay? I don't know what you were expecting, but you should expect a straight line through 0, 0. Okay, because you should expect your perceived depth to go with real depth. You know, if an object is twice as far away from you in the real world, you'd like it to be twice as far away from you in the perceived world. Otherwise, there are problems. So this is a distorted view. That happens, okay, and that's why people look at 3D, bad 3D, and they say, wow, that's a bit odd. It's a bit odd. They don't know what it is, but it's a bit odd, okay? All right, so can it ever be correct? And the answer is yes, okay? It can be correct. But only under one condition. Only under one condition. And so we have this condition. This is the correct condition. The correct condition is when the separation of your cameras is the eyeball separation. Okay? And a lot of people do that anyway. So that's a good thing. But unfortunately it isn't, because what they don't do is adhere to the rest of the stuff. Okay? What they don't typically do is show it on a screen that allows this. This says that my fixed separation has to be the eyeball separation. All right, so the eyeball separation on average is about 65 millimeters. And if you separate something by 65 millimeters, which is about this big, on a screen this size, it's impossible to see. Okay? However, on a cinema screen, it represents 12 pixels. All right? So it is extremely small on a cinema when it comes to angle subtendence. But when it's on something this size, it is huge, okay? So this criteria is a bit screen size dependent, which is something that has to be taken into account. Finally, you must set the zoom to be 1. All right? You must view something as if you saw it. And there are very few things that you actually do that, and I'll come back to zoom in a minute. So in the end, what you do is you set up your cameras, and these are meant to be the lenses of your cameras and the sensors of your cameras, to do this, which means your eyeballs subtend an angle with the screen, and you make sure that the cameras capture with the same angular capture. Okay, and also overlapping at the screen. So this is the geometrical perfect situation. But the demands of this is a problem, because this is a problem on small screens. You can't make D equals E for faraway objects, trust me. All right? If you had a cell phone, you'd have one image, and then the other image would be somewhere in space somewhere if you separated by 65 millimeters. So it's impossible to do something like that. So this is so cinema is much more forgiving. Secondly, zoom is not typical, and I've got a slide here that explains this. Okay, so zoom is simply this. I mean, I don't have to explain to you what zoom is. This I've assumed is 1, okay? It depends how you capture things. But once again, it's like if you had a frame of what you have on your desk of your family, let's say. You should only put a picture in there as if you could see your family while holding that frame, okay? And that's what you don't do. What you do is you typically capture it with a wide angle. You put it in a photo frame like this, and you put it on the desk, and you look at it from over here. And somehow, everybody is very happy with that, okay? You would never see that. You'd never ever see that. Because the objects are far too small in the background for if you were looking through that aperture. Okay, that is completely incorrect for a 2D. But we've said, no, I understand. I can map what the world is. I get it, No problem at all. We'd have no problems with the fact that, this thing is starting to curve at the edges here. So even in 2D, there's incorrect. So if it's incorrect with 2D, you've got to ask yourself, what the heck do you do with 3D? Because what happens is that when you capture things with a wide zoom, which is typical, play it back on a narrow zoom for your eyeball and the screen, then the objects in the background are far too small to what it would be. Okay? So where do you put them? Do you put them where they think they should be? Or where, in actual fact, there is no correct way of doing it. No correct way of doing it. All right? So, you've got to ask yourself what the heck you've got to do. And this is quite an important phrase, okay? While people gradually get used to what will be standard practices, all right? So eventually, people will see 3D and say, that is 3D, that is 3D. There's no, it's just like, look at my camera, look at my family here, okay? So this will happen. People will get used to the way 3D looks on screens, and then it'll be perfectly all right, and people will wonder what was wrong with it, okay? But until that happens, we have to make an effort to try and work out what will obviously be wrong and what will be acceptable. So we have to try and understand what is it we perceive as depth, and how do we capture things accordingly. So what is it? Well, there are 3 things that 3D depth is giving you extra, okay? One is perspective. Or at least it should give you perspective. And what perspective is that the on-screen size of similar objects should be directly proportional to their perceived depth. All right, so if I have a person on my screen that is this size, and I have somebody standing, let's say, 10 yards behind, and he is this size, and he will be a certain size in real depth. Okay? When I play him back on my screen, if he is not the same percentage, same fraction away from the camera, he will look as though he is in the wrong position in depth. There's a conflict between real perspective and what you actually see on screen. So the idea is that we should we might want to try and preserve this perspective. There's another thing which is actually different from perspective. It sounds very similar, which is roundness. Roundness is a very difficult thing until you see it. What this is all about, that objects have a certain height to depth ratio, like heads in particular. That's why it's called roundness, by the way. This was a phrase brought up by somebody called Phil McNally, who's at DreamWorks, and he had a ball that he was breathing, but it's actually meant to be a head, because everybody is so focused on people's, the nuances of people's features. You can tell whether people's heads are flatter or not. If you put a film up that has the wrong roundness of somebody's head, it's very, very obvious. So what you want to do is preserve the height to depth ratio. And objects should appear at the correct depth relative to their height, not flat or pointy. Maybe sometimes you do for effect, but in actual fact you don't want to do that. Finally, there is a size issue, which is sort of amazing. I mean, I went through these things. It turns out that on a 2D screen, you can do anything you like with size. Okay, you can build buildings with the size of little buildings, and your brain says, no, it's okay, it's over there. However, once you place it in space, it seems to acquire a correct size. So that if an object is this size and is meant to be a building, it better be way back there. Because if it's here, right in front of your face, it looks like it's a little model of a building. And you have a little plane like this. Or you have a head that is this size, but is a long way away. It's like this guy's huge head, you know. And it's very uncanny as to the fact that that is the case. So somehow you have to accommodate size as well. And it turns out that you can't have all this stuff unless you're correct. Okay? Just perspective, these are two cars. If you have a height here on the screen, a height here on the screen, those heights are determined by the camera. But your perceived depth should be in relation. And what that means is your perceived depth should be proportional to your real depth. And you can do that. And you can do that for various camera separations. Okay, this is just a series of straight lines. What you end up doing is this. Okay? Now the point of doing this is that there isn't one solution with perspective. There isn't one solution. There is the correct solution. That has perspective because it's correct. But there isn't only one solution that has perspective. But what you do is you end up with different sizes, for example, and you have different roundness. Okay? So it doesn't mean it solves everything, but it does preserve perspective. And that is quite important. And what you get with perspective is a uniform object scaling. In other words, all objects, if they're big, they'll be equally bigger than they are in real life. You get uniform roundness depending on the zoom. They'll be flatter or pointier all the way throughout the scenes. And that's quite useful because your brain is quite used to sort of global mappings of stuff. But it's not really an object-based approach. If you end up with perspective and some actors, because you concentrate on the people talking, if they don't have round heads, then you've got a problem, even though it preserves perspective. So you end up with, and the issues with perspective, sorry, I'll get to what I was just saying in a minute. The issues are that you can get large disparities. Here's the guy poking your hands out. No, you see the separation is very, very large. Also, you can get very flat objects. I don't know whether you've seen a lot of 3D, but sometimes you can get a cardboard cutout effect. Again, you have to see to believe that. It's unfortunate I don't have 3D here, but this is Austin Powers here. This is actually literally a cardboard cutout. Okay. So in the end then, for cinema, you really ought to try and get perspective for large scenes that are seemingly uniform. So your eyeball doesn't point on any one thing. Then a global uniform mapping is actually very, very good. So you end up with trying to do that for large outdoor scenes. And if you can do it correctly, then do it correctly. For soccer, you can actually do it correctly, the ones I've seen. And it's very natural indeed. But you can get away with different flatness and different scaling for large scenes. However, as soon as you bring in people in particular, or anything you're focusing on, you're going to have to start concentrating on that object. And you end up with having to calculate how to preserve, in particular, roundness at that point and size. Okay, so I'm gonna move on because of course I'm running out of time. Right, smaller screens. Now we got a problem. All right, now we can't have perspective. Forget it. End of story. So if we can't do that, what do you do? Well, you can't really preserve roundness either. Trust me. You end up because everything is squished, and as soon as you squished it, you really have huge distortion. And that distortion is going to be a problem. People might have noticed, I don't know whether anybody who played 3D games on the NVIDIA system, okay, you're going to have to believe me. Initially it's quite an experience. You go through this 3D world and you actually navigate where objects really exist inside the screen. But eventually you realize you're concentrating on a gun. Let's say it's a shooting game. And the gun is a highly interesting thing because it's really long and really big in the frontier. And then you find that you're not actually looking at what you're shooting at because the rest of it's like a wallpaper behind. It's absolutely flat at the back, okay? And that's because if you just render with two standard cameras, you will get that distortion. That curve I showed you, which flattens off, is absolutely the case. So you now have to do something different. And this is where RealD has come up with a solution which we believe is optimal. We do have other solutions, but we believe there's an optimal one. And we think that if you've got a limited amount of depth, which in turn means you're going to restrict the separation on a small screen, then you ought to do the best you can with that depth. And to do that, you should do that at all times. And so these are just two equations which force your disparity, the separation of your images of objects that exist at the maximum minimum of your scene. All right? So if you put A equal to this and D equal to this, then you will always get the object that is at Zmax at this separation, which would be Dmax, and your object at Zmin will always have Dmin, okay? Whatever you do, all right? This is the solution. And you'll always get the best bang for your buck. But you will get depth distortion, okay? And this is where, hopefully this is where, this is a conventional rendering of a, it's like the NVIDIA game. You take two cameras in a 3D, this is a real game. This is the ultimate, what's it called? Oh, cranky. Ultimate Tournament, I think it's called. It's the Unreal Engine, yeah. So what you should notice here, what I've done, I can't show you 3D, so what I've done is I've done motion parallax. I've taken a camera and I've moved around and rendered the different images. And what you sort of try and imagine that one eye is going to see, let's say, one extreme and the other eye is going to see the other extreme. But the point of this is that by the movement, the relative movement of things, you can see whether there's depth or not. Because if objects are in the same place, they always stay the same. If they're different, they will start moving relative to each other. And you notice that this building here, for example, relative to that, there's no movement at all. The front of this, this is the top of the building. This isn't a very good video, unfortunately. Has no movement relative to that building relative to that one, relative to that one, no movement at all. This whole thing from about this distance here has no depth in it, absolutely nothing. Okay? So this is your painted backdrop with what is a considerably large cannon. I mean, some people would like that, but it is a very, very large cannon. All right? So what to do? Okay? So what we do is we have a computer-generated solution where we pre-distort the world model to give a uniform scale depth and a constant roundness. Okay? And it turns out that that is a very good solution. And in order to do that, we've developed a framework. The framework is the understanding that if you take this situation, okay, you've got a camera lens, you're going to render this image, okay. In a computer, you have a virtual camera, but it works the same, okay. You have essentially a lens, and the rays go through the center of the lens, and it just maps intensities from objects onto a sensor, which then becomes your 2D image. So this geometry works. If you have an object at Z, then it will give you an image of this particular apple on your camera or on your screen of the following. What you can do is you can say, oh, well, okay, I'm happy with this image, but I'm now free to change where this apple is as long as I scale it both in X and Y as well as in Z. And I will have no effect on this image, okay, to first order. So if I do this, then I can guarantee that the 2D images that I capture are going to be the same, which is good, because obviously if you walk around the world and you're rendering these images, you want to see those 2D images correctly. But what it does do is it puts this object in a different, real position. And of course, when it comes to rendering, that real position is now what goes into the equation, which gives you perceived depth. Okay? The only thing to realize is that you actually scale it to the point between the virtual cameras, not actually to one camera. If you do it to one camera, well, you could do it to one camera. The other one, there'll be an asymmetry in the whole thing. But nevertheless, we scale it to the center of the two cameras. In doing that, we can move objects so that they're... I thought there was another one in between here. Obviously not. Okay. All right. So we can move objects to where we would like them to be, such that when we do render them, they will be in the correct position for giving us the best we can do on a small screen, which is uniform roundness and uniform depth. So we end up with taking a new curve, or calculating a new curve, which is the perceived depth of the new position which in turn is a function of the previous position. Okay? So for each point in this world, we are going to give a new position, depth, and we're therefore going to produce a curve like this. But we're going to say that at any one depth, actual depth, we would like it to have the desired roundness. All right? And the desired roundness happens to be the straight line. It's the perspective line. It's the one that goes through 0, 0. So in order to determine what the best mapping is, this function z prime, we try and relate the desired mapping, the desired gradient here, the desired depth. I should say that the gradient of these curves is the depth. All right? It's the change of perceived depth with actual depth. Okay, you'll have to trust me. Okay, so you take the gradient of this thing and you write down this equation. Okay, you say that the gradient of our new function now should be a fixed factor of the desired. All right, and you can solve this equation. You end up with something like this. Okay, and this is interesting because it is a unique solution. There is only one solution where you pin the two sides, and so this happens to be the solution that we are now implementing in games. Because what it does do is it means that given a depth on a small screen, we have uniformity of depth. Whereas in real life, let's say you'd have a meter between two objects, a perceived meter at a certain amount, you now see a perceived fraction of a meter, let's say 1/10 of a meter. And that can be over there, or a meter here would be a 1/10 of a meter, where the new perceived objects are. All right. So throughout the depth in your screen, it is a uniform mapping. In other words, if you have flat heads, they'll be uniformly flat all the way through, which is obviously not optimum. Well, I shouldn't say optimum. It's not correct, but it's the best you can do. It's better than having some people with very pointy and absolutely flat on the back end. It turns out to be very successful, actually, this particular mapping. And the way we do it, and this is where one way of doing it is to literally distort the world. This is a top view. We use a program called Maya. I don't know whether people are familiar with that, but it's one of these 3D rendering tools. Here I've got a little camera down here. These are supposed to be asteroids. These are the only things I can draw, actually. But we have, various asteroids, one close to the camera and various further out here. And you find that if you take a stereo pair of this, all these objects here are essentially in the same plane, and then this one's rather elongated close to you. What you do then is you calculate the optimum new value of z prime for every z, which moves the points. These are made up of vertices and textures. You move the points. Now you notice I haven't moved them all. This is because it's quite an overhead. The Maya plugin, as it were, only moves the points you're actually going to render. But you've got to see that this object has now turned into something that is highly elongated like this. This object here is now down here. This object here, the bits you can see are down here. So what you're doing is you're actually moving things quite a long way. This is just the way you move it in the computer. And the problem with that is that the textures that map between the vertices now become highly stretched, and you find that you get texture tearing. So this isn't a very good way of doing it in the end. It's actually better. Oh, no, so before I just go to this, but once you've distorted, you can take left and right eye images together. You don't have to distort twice. So that's the advantage of this approach, that you literally put the bit of the object that you're going to see into the right position so that the left eye camera can take a picture of it and the right eye camera can take a picture of it, and it will be corrected. However, because of the movement, this turns out to be a better way. It's a better way to say, you know what, I know what happens. The images actually move slightly. I even know the direction of which they're going to move. So why am I moving these objects towards me and scaling everything when I could just move the objects slightly in real space, and distort it slightly. And the advantage of that is that the shifts are much, much less. Okay, so this is meant to represent two cameras. This is a point that you're interested in, which is at a certain distance away from your camera. And you say, I now want to move that point to a better point, closer to the cameras, to give me the correct perceived perception when I take my stereo pictures. And in the old method, we would move it over here, okay? If we move that over there, then you can take the picture of that point in this camera and in this camera, and it will give you the correct point on your images. However, you can move it anywhere along this line here, because this line will put the intensity on the same position sensor. So it's easier to move it laterally. And it turns out that there's a huge advantage in terms of the shift. And I just want to show you this quickly, I'm sorry. This is a top-down scene of an object out here at 200 units. And in this little square here, we have another object. Okay, you've got to try and imagine that in here, we have a unit at 10 units, an object at 10 units, another object at 2 units, and one object really close at 0.1 unit. Okay, so this is a very deep scene. It's obviously to bring out this whole effect. But this isn't a ridiculous scene. I mean, this is a 2,000 to 1. It's like having an object at a meter while having something at 2 kilometers away, which is not ridiculous in a lot of cases, but it is a bit extreme. If you carry out our algorithm on this, you find out that you have to move, well, you move both these objects. You keep the ones at the end because they're at the limits. But this object has to move this much, okay, 0.036, okay, at a distance of 10, which is very, very small indeed. And in fact, if you look at the mapping in general, you have to move these points laterally now by fractions of units, not even 0.1, for all the vertices out to your maximum distance. So it's a very small movement, but it has an effect. So this is a superposition of left and right eye images of the scene you've just seen. Okay, they're a bit artificial. We've got a cone, I think this is a cube, and this is a cylinder. If you took the pictures without doing anything, you find that the separation of this object, this is essentially the same. Okay, so they're all flat, all the way from a distance of 2 to 200. Okay. When you correct it, the very small amount I showed you, you find that there is now, and of course I've done this, so that they're actually linear here. Okay, so there is a clear stepping in depth of these things, and this is then the video of the corrected one. Now this is done in real time. Okay, so now the difference, the relative motion of these things, the relative motion of these objects within the plane here are all shifting. Okay, so you find that the gun is still moving as you'd expect, and the front of this relative to that. So when you turn this on, okay, you're looking at this world that has this large gun with a flat thing at the end. You turn on, what you find is the world comes out like this, and the gun does like that. Okay, and suddenly your concentration is in the game instead of being outside, and it is so obvious that this is something that we're actually commercializing at the moment. So this, as you recognize, by some people, is the Unreal Engine. The Unreal Engine is used for many different games. I can't tell you exactly which games are going to come out, but it has been implemented at the engine level. It operates in real time. This particular game runs at 30 frames a second. It is licensed for games set for release in 2011. I was hoping to actually state a few of them, but we're still sorting out some of the details. And of course, it can be applied to any CG rendering platform. And in the little spiel I gave you, the people in Hollywood do this by hand. Okay, they actually physically take heads in particular, because they're very important, and move them in the scene, exactly how I explained that scaling thing. But they do it by hand. They say, does that look okay? Yeah, okay, so put it in there. So in some ways, what we've done is we've automated it, which of course you have to do in a game. In a game, you don't know what is better or worse. You have to do it on the fly. And so we have a totally automated method of giving you the best bang for your buck for computer games. And that's something that hopefully you'll all be playing. So, questions?
Do we need to separate objects?
No. We do it on a vertice by vertice game. Yeah. Now there is a problem with sparse vertices. So floors that have just 4 points on the corner. If you just move the 4 points, it doesn't preserve straight lines, which originally I was a bit worried about, but it turns out that you don't really notice it because it's so gentle. It really works quite well. But if you have a floor that you only move the top vertices and the bottom vertices, and you find that the objects within the depth between the closest point and the furthest point will move differently. And so you have the effect of objects lifting off the ground or maybe sinking below the ground. Even though the 2D, close one eye and they're on the ground. And then they sort of, so what you do is you have to populate large areas with extra vertices. But that is routine. That's why at the engine level you can talk to the game developers and say, this is one of the overheads. But you're talking about many tens of thousands of vertices, so adding hundreds here and there is not really a big overhead in the performance.
The user thought you mentioned that your users may be mining from tourism.
Yes.
So it looks like that you're switching to also mining from licensing IP, right?
Yes, well, you know, it's all words, isn't it? I suppose what we don't like to do is make too much and sell the thing, okay? So a licensing play is more what we do. As a company, we try to be a licensee. Having said that, we make the cinema stuff. And so we do make it, we just don't sell it as a sort of commodity. We sell a license. We sell a license to use 3D technology in theaters is another way of putting our service agreement. So yeah, it turns out that manufacturing, unless you're, well, the world has become, you know, the Far East produces these things, they produce them extremely cheaply. And unless you're going to become a company like that, you know, it's very difficult to make money that way. So that's part of the way we survive, I suppose.
Do you get the whole sensation of depth through in the brain, the way that the brain processes images through the stereoscopic effect, or is there a little bit left in the process of accommodation
Yes.
in the eye and defocusing in the image? For example, you know, a screen in a cinema is, you know, a good distance away, and even if you wanted to present something as being
Yes.
nearby, you're still focusing
Yeah.
on something.
So I don't know whether you heard. The problem you brought up here is one of accommodation. Accommodation is this business of you've got a lens in your eye, and objects that, you know, appear through stereopsis to be here should be focused here, but everything is focused on the screen. So there is now a mismatch between what your lens thinks and what the screen thinks. And you're absolutely right. In the cinema, it's much more forgiving again. Of course, unless things, you know, go straight for your nose or something. But that is a problem for small screens. If you do a calculation on the resolution of the eye and how much depth you can accommodate, after about 4 meters or 5 meters away, it doesn't really matter. So if you get a large screen TV at 5 meters away, then you can argue from, you know, the physics, you know, the point spread function that you can resolve in the eyeball. It can't be a big problem, and it doesn't appear to be when you look at big screen TVs. However, when you're holding handhelds, it is a problem, and that is part of the reason they think there is a limitation on the depth that you can get. You know, I explained that you can't have the eyeball separation, which is well, obviously you lose one end of the image if you do that on a small screen. But even when you can accommodate, not accommodate, that's a bad word, when you can imagine being able to cope with separations on the screen, there's still a problem when you get closer and closer to the eyeball, because we think, due to this accommodation problem. In fact, all this 3D, the reason why 3D is difficult to create in this case is that you are trying to fit in with what you are used to. And you can't do it perfectly unless you do certain things. But people will get used to it, just like they have with 2D. So it's a time getting used to, and yeah, we do this and do that. So at the moment, it's a sort of best practices thing. And we've come up with, you know, guidelines, as I say, for a capture, direct capture, and when it comes to CG, we can do better. And I should say that the techniques that I told you for CG, which they are using in Hollywood by hand, are the reasons why the animated films are so much better in 3D than the live capture ones. In fact, Avatar, the scenes that were captured with real cameras are clearly distorted relative to the ones that are completely rendered automatically. Not automatically, using computer graphics.
So what's the optimal place to sit in?
Well, it's designed to be around the center. I mean, if you know, all the cinemas are slightly different. There is a problem with very, very wide angles. So if you're sitting on the periphery, that's a problem. So it's designed to be sort of halfway up, but no cinema is the same. So I can't tell you exactly for any one film, but certainly very close in on the sides are not very good. A lot of 3D cinemas now being set up such that there aren't many seats on the side. And you know, getting away from the screen is a good idea. But you'll find that if you're close to the screen, things are a lot flatter than if you're further away from the screen, even though they're more in your face. You know, so it's a little bit uncomfortable. It's better if you go further back. Yeah.